I hope my screen is visible for you. Okay. So the ultimate aim is to get the functions or formulas for the deflection, to find the deflection for the various actions of the on the beam. So that action may be considered by referring to axial loads, bending loads, shear and torsion. In previous class we have discussed the axial load and bending loads. So due to that axial and bending, the total strain energy we have obtained. The total strain energy we have obtained, and in this class I would like to discuss the shear and torsion. So before going to learn shear and torsion, here the basic things must be known. So what are the basic things here? The basic things are the modulus of rigidity, modulus of elasticity, right? So Poisson's ratio. These are all the equations, whatever we have learned as an elastic constant in the previous semester, that must be well known because they plays an basic things to understand the strain energy that is stored in the body, right? So here, so if you see for shear stress, that is for shear. So for shear, uh, what exactly the happens? What exactly in the beam the shear get happens? So if you consider a beam, say if you consider a beam or any other member, right? For a shear. So on this part of the beam, if you consider a section where the shear force is acting, if I see the particular part here it is acting as a shear force section, the beam may be having a continuous length in this part. Since we cannot consider at the center of the beam, since it is the less shear force that may be happening. So on this case, if you see the shear force at the support, near the support, the once the shear is happens, what exactly the phenomena that is going to be there is the part of the beam, the part of this element will try to move either downward or upward, which is opposite to the part of the other section, right? So that means when the shear is happened, the particular part of the element that will trying to move in this part. Dear students, I will be get back in a 2 minutes once again.
So तुम्हारा
Okay, sorry for the inconvenience. See, if the shear force is happening, if the shear force is happening at the section, the particular part of the element or a beam is trying to move in either direction, which is in opposite, right? Which is in opposite direction. I hope it is a very basic things. We know that when the shear is happening in the element. So once it is happened, if you see the load that is acting on the beam may be in either direction, either this one or this one. At a time, both the forces will not act. If the both the forces are acting, there will not be any shear force because that is an concurrent forces that is acting on a same point on a plane. So that is the concurrent forces which are in opposite direction. So in that case, we cannot have the shear force, but either of these one force is acting on the beam, the particular behavior of the element that can be seen. So if it is happening, uh, the deflection will be happened at this point, right? The deflection is happened at this point. So since it is, if you see the axis of then the graph, it is an y-axis you can see, and it is an x-axis. Am I right? So once it is having the axis, this particular deflection, however, we know that the deflection we are referring with the delta, and delta y we can write. Am I right? Because it is in a y direction. This much of deflection we have observed, that is due to the shear on the particular element. We are not saying only it is a beam. In any of the structural members, we can expect the shear force. So here the delta y is a deflection that is happened in the element due to the shear. So once this deflection happened, there might be an angle. There might be an angle that we can say theta due to the deflection. That is, I can write delta theta because the deflection that has happened, and due to this deflection the angle is formed. That angle is delta theta, we can say, right? So this delta theta is for the length of an element. So in the element, in the total member, we can see that is the length of the member. Say for example, if you have a member, so if in this member it is referred or denoted as L, that is the length of member. But here what we can observe, in this case we are just referring an element in the member. Element in the member sense, it is a part of, it is a part of the element, it is a part of the member of the, that is what we have considered. So this is the element in this member, that is what we are referring. So once we know that the per element, later we can go for the total member, that is by integration from 0 to the length of L, right? So this is the procedure we are obtaining to have the complete total strain energy that is stored in the body due to this shear or due to any other forces. So now we are dealing or discussing with the shear. We are now considering for this one. So this might be, or this I could say, that is dx instead of, it is that it can be considered a dx, right? So this is a dx, since it is a dx and this is a delta y, and this dx, for the length of dx we got a deflection, that is delta y, for the length as an result we are forming an angle delta theta. So this is the basic thing. So whenever it is asked to write show that the equation for shear stress, the strain energy for the shear stress You may have to draw the diagram and you have to explain the things, that is delta y. Due to the shear force, we have got the deflection in the y direction. Due to this deflection, the angle is formed, that is the delta theta. Delta is associated with the theta is because the angle is formed because of the deflection. So now once it is known, now we are aiming to know that the total strain energy, right? So what is total strain energy? So here, please dear students, you please keep in mind that, so whatever the load is acting on the member, whatever the load is acting on the member, either it may be an axial load, shear, bending or torsion, any other load, these are all loads are considered acting gradually. That means, see, if you consider an axis, if you consider an force, so in this part, we are referring as an total force that is acting on the member, and this part we are getting the total deflection. So for the total force, we are getting the total deflection. So how exactly the particular part of this is happening? So now whatever the consideration or assumption is there, that is gradually acting. So if the load and deflection are gradually are the same at the any level, that means the load is applied gradually. So since the load is applied gradually, the axis or the length or the member will be having the coordinates in this manner. In the x and y direction, we have considered deflection and load respectively. Once it is considered, the form, that is the graph, will be formed in this manner. If it is a graph, if you see the area of this, so this is the total load and this is the total deflection. So total, what is the total strain energy of this part? This is the graph that may be referred or that may be representing any other members, any of the member which is tested and plotted here, that member's strength. Correct. So this graph is having the area, right, which is in a triangle. So the area of this triangle will be half base into height. Am I right? So this is the total strain energy that I can show with a U. So this is the total strain energy, which is half base into height. So base is the total deflection that has happened because of the load. That means this is what we are considering, the load is applied gradually. Correct. So now in the place of this delta, what do we have, that is delta y. Am I right? So in the place of delta, we have the delta y, that is what I am writing, and multiplying with the F. So F is a force that is happened or that is applied on the member. So I can directly write as it is as a F. So the total strain energy in the element due to the shear force, that can be written uh, at the initial stage, that is half delta y into F. So now if you see the delta y, so what we could write as a delta y over here, this is a delta y, right? So if you see the delta y, so what we could write, so for delta theta, you observe the delta theta, which is the result of this, effect, the effect of shear, and the delta y is also an result of the effect of shear. At this level, if you see the relation between this delta y, delta theta, and also it is depends upon the dx. So in that case, if I write delta theta, which is equal to delta y divided by dx, which is the length of elemental length. So if you observe this equation, the delta y could be written delta theta into dx. delta theta into dx. I hope, dear students, you are getting what I am discussing here. So this is the delta theta, delta y. So this can be substituted in the place of delta y. So if you substitute, the 1 by 2 will be remain same. I will just rearrange the term f here, and delta y could be written as delta theta multiplying with dx. So this much is the part we can expect. So later on, if you see particular relation, the particular relation of this delta theta. So delta theta can be written, can be considered, since the phenomena is discussing for the total shear, that is shear stress and the shear strain. So what the exactly equation do we have is the modulus of rigidity. So modulus of rigidity, what exactly it says? The shear stress to the shear strain. Shear shear stress shear stress to shear strain, right? So this is the modulus of rigidity. You have already gone through this, and you people know at shear stress and shear strain. So modulus of rigidity that expressed in this manner. So this shear stress and shear strain, how we could write the shear stress, that can be referred as a tau, right? And the shear strain that can be referred as a delta theta. So now G equal to tau by delta theta. So here, that what is tau now? Tau is a stress. Tau is a stress, right? So that is shear stress, not only the stress which is not a sigma. It is a tau which is a shear stress. So the shear stress that can be considered, that can be referred the force by area, or else the total stress, that may be the load by area, like that. The total stress, the shear stress tau, that can be written as F by A. So now, by referring to these all, that is G which is equal to tau by delta theta, and F by A is nothing but the tau. So substituting the F by A in the place of tau and rearranging the term equating to delta theta. So what we could refer, so by F by AG, right? So now in the place of delta theta, we can write F by Ag. Why we are considering this F by Ag is because we are referring to the strain energy that is due to shear. So the shear strain energy we are referring and we are speaking means we need to consider the modulus of rigidity of the body, or the element, or the member what we are referring. So once the modulus of rigidity is referred, the shear stress by shear strain is an equation. So in that equation, the shear stress is written as a tau, as we refer and we denote it with a tau, or the shear stress is nothing but the load by area. And later the shear strain, the strain is nothing but the change in dimension or deformation taken place. Deformation taken place because of shear, since the deformation, that is delta y, we can refer. So delta theta can be written as F by Ag, and substituting in the equation 1 by 2 into F multiplying with F by Ag, F by Ag, and remaining dx, and remaining dx. So now this is the total strain energy in an element. Just I will again write it as an F square by 2 Ag, F square by 2 Ag into dx. So this is the total strain energy in an element. So now we need to know that the total strain energy in the total member. So for that reason we need to integrate it from 0 to L, that is F square divided by 2Ag, F square by 2Ag, and with respect to the length. Why this dx is remained here is because this is the dx value, this is the dx point as the length of the element. If this with respect to x, again because this dx is the main part of the element we are considering, if it is varies, again the delta y and delta theta is varies. That means that is the part that is depends and that is acting on the element. So now this F square by 2 is into dx, that is the total strain energy stored in the element due to the shear force. Dear students, I hope the discussion is clear for you. If you have any doubts regarding this discussion, please let me know. Else, I will start discussing the total strain energy due to torsion. Please, anybody if you have doubts, ask me now. Yes, dear students, no doubts? Yes, anybody? Arun? Yes, is that clear, the discussion? Chandrika, please,
Yes, sir.
please let me know that whether you understood or not, all of you.
Yes, sir. Understood.
See, it is not like that I need to call everyone's name and ask everyone's. Please, if you have any doubts, it is free for you people to discuss over here. And don't think anything. Don't think about the part whether you are wrong or correct. Okay, Monica,
Yes, sir.
yes, are you listening?
Yes, sir.
Okay, is the discussion clear?
Yes, sir. Clear, sir.
Okay. See, why I'm asking you people is because in every examination, the questions on the total strain energy stored in the body due to axial, shear, bending, and torsion. In either of these, any after one derivation will be there for your examinations, and later on you will be having the problems on this part in your module and in this fourth module. If you understood this derivation, then only we are able to calculate the total deflection in the beam. Correct? So that is the reason I am trying to explain you here. So now, uh, I hope this is completed, and later on, I would like to discuss for the torsion. So before that, here I said that I am discussed that is the load is acted gradually. If the load is acted suddenly, because this concept, if you remember thoroughly, the part of the discussion is already studied, that is in the strength of material subject, that is the load applied gradually and load applied suddenly. So the relation between these two is, if the load applied gradually, it is the half of the total force to the deflection, which is the half of the total force to the deflection. And if the load is applied suddenly, so if the load is applied suddenly, what we could expect the graph, what we could expect the graph is, so here this is the direction of x and y, and here in the direction of x we got delta, and in the direction of y we got force. So this is happens with an sudden, because the sudden in the sense the load is acted at the intensity suddenly on the element, and due to that sudden element there is a sudden displacement happens. Because say for example it is having a 10 kilonewton of force at this level, and on a member, if you apply a sudden load of 10 kilonewton, either it may be axial or it may be a shear, any other member, any other parameter that may be considering, but the phenomena of acting the load is sudden, and that case the deflection will be happening suddenly with the point. So with this load, the particular point or the particular stress that may be expected, and the deflection that may be expected like this. So the area of this one, the area of this particular part of the element, that we could write, that is the strain energy of the body will be F into delta, right? F into delta. Because now if you see here, the load applied gradually is half of the delta and F, that is half of the deflection and the total force. But the load applied suddenly will be the equal, R is equal to 1. The relation between these two will be there in your every competitive exams. Most of the times it is there, it is asked in the multiple choice or multiple choice questions, MCQs. In the competitive exams it is asked, it is being asked to write or to give the difference between the load acted gradually and load acted suddenly, right? I hope you got this, the strain energy how we are considering. So now the torsion is remade. So in this torsion, if you see, before going to this the particular part of the torsion, we must remember we must remember the equation. What is that equation? Can anybody guess the torsion equation that can be referred in this derivation? Yes, T by I, G theta by L. Do you people remember that
Sir, P
equation?
theta by sir. Yes, sir.
Yes, yes,
Yes, sir.
very good.
What is the small yes, sir.
Yes. So by referring to that equation, by referring to that, now we need to solve for the equation for the derivation for the shear stress, that is shear strain energy because of the torsion. So now, if you see how exactly the torsion can be referred, so this is a particular element which is fixed at the part, right? And here we are referring the total torque T, right? And if it is an axis, if it is an axis of an element, if it is an axis of an element, here due to this torque we are having, or we are getting the particular angle, the particular angle that I will say that is d theta, right? That I will say d theta, and which is the dx, which is the dx, correct? So because of this total torque, so whatever I am drawn here, that is an element in the member, that is the reason I am writing it as a dx. If it is a total member, I could write it as an L instead of dx, right? So this is an element. So in this element, if you observe for the total strain energy, again the load is applied gradually, and the total force here, what is the total force? The force are the part of the force that is acting as an T, that is torque. So now the T and this one, the displacement, are the, because displacement, that is delta here with respect to this torque is d theta, or else you can write delta theta, no problem. That is the just notation we are observing. So d theta can be written, correct? So now once we know that the equation for the strain energy that is due to the torsion, that we could write for d theta. So d theta can be referred by the equation, the torsion. So what is the torsion equation? We have T by IP. So IP is the polar moment of inertia. The polar moment of inertia is nothing but the moment of inertia in either of the directions, either x and y. Either of the direction, that is the polar moment of inertia. I hope you people remember, because the basic things why I am stressing over the things is because this is the reason we must know the things what we have learned in the previous semester. It is not to, you know, pass over the exams only. This is those are the concepts we must remember and understood to understand the further things. Correct. So now this is the tau by IP. So tau by IP, that can be referred with the g theta by L. Correct. So here if you see, the L is nothing but dx. L is nothing but dx, and theta is nothing but d theta. So g d theta can be written for t by IP. So now we are referring for g, and that is d theta. We are referring for d theta. So this equation can be rearranged and rewritten with t dx, which is multiplying with p dx, divided by g ip, that is g ip, right? So this equation can be substituted in this one. It is a very simple thing, but the important point here is to know the basic concepts. E dx, again we are remained with the x here. That means the length of the member, that is the most important thing that is considered for the d theta and the tau. That is the main point. So now I can write it as a t square by g ip into dx, since again it is for the element. So if you want to get it for the total member, just we need to integrate it to 0 to L. So 0 to L is t square by g ip into dx. So that is the total strain energy in the body due to the torsion. Dear students, we have completed all the four, equations. So now I will just recall those things. I'll just recall those things so that you people can remember on this. So for that, I will write it for axial load. So for that axial load, so now for bending, that is due to bending. Directly I could write it as due to bending. And now due to shear. So now due to torsion. So what is due? It is due to torsion. Why I am writing it is everything is, that is the total strain energy, total strain energy stored in the body. Total strain energy stored in the body due to axial load, due to shear, due to torsion. So if you see these things, the due to axial load. Can anybody tell me what we have derived yesterday? Yes. Can anybody tell me due to the axial load what we have derived? I hope you people have taken the note on the discussed things. If you have taken the note, please let me know what is the total shear strain, sorry, again, strain, total strain energy due to the axial load. Yes, Chandrika? Yes. Anybody? No problem. If you don't know, let me know that, then I could write it again here. Right? And that is good use and separating false. So for this, so total strain energy 0 to L, that is the F square into L divided by F square L R F square dx equal to 7. Since we are referring to integration, F square by 2 AE, right? That is to the dx. So now due to bending 0 to L, m square, that is the moment, because bending we are referring moment. So 2 EI with respect to x. So again, due to shear, what we have derived now, 0 to L, 0 to L, F square divided by 2 kg into dx. So due to torsion, what we have derived, 0 to L, T square by G IP, again with respect to dx. Again with respect to dx. I hope all the four derivations you got clear. Okay, is that clear to you, students?
Yes, sir.
Okay, now on this part, in the with the continuation with this, we will be having the problems on different kinds of members, both truss and beam, both on truss and beam. So on the truss and on the beam, you need to calculate the deflection due to the various actions. That is by referring to method of strain, the total strain energy. And that is one of the method we are referring for the calculation of deflection in the beam. So with this note, I would conclude this class. In coming class, I will solve the problems on the beams, that is on the determinate beams, to calculate the slope, sorry, deflection due to by referring to the strain energy. Okay. So if people have any doubts regarding this, please let me know. Else, I will conclude this class. Yes, dear students, Afrin, are you
Yes, sir.
listening? Yes. You got the concept clear?
Yes, sir.
Okay, fine. Okay, Girish Tarikoti, are you listening?
Yes, sir.
Yes. One more thing, please everyone, whatever we discuss in the class, have a pen and paper and make your notes. And later, once the class is over, you can go to that and you can recall over the things. Okay, that is the suggestion what I could give in this class. So, okay, dear students, in coming class, we'll start the discussion on the problems of the deflection of the determinate beam and their stresses by referring to the strain energy method. Okay, with this note, I will conclude this class. Thank you everyone for attending the class. Thank you all. Thank you.